Great. Let's start. Today is going to be about the rest of chapter 2.1, and then we'll start with chapter 2.2 because we don't have much time today, so we're just going to go ahead and start. So you see here on top of my head, there's the topics for the day. So there's going to be 3 short videos, each about 15-40 minutes, and then quiz number 7 is going to come up. Good, so let's go ahead and start. In the meantime, if you have any questions, feel free, just type it up on the live chat. Great. All right, secure TCP. This is the next topic. Yeah, if you recall, when we were talking about these service requirements, right, there are 4 of them. Reliability, which is supported by the TCP. Delay requirement, right? It's somewhat supported by using UDP. Bandwidth requirement, and that might be better supported by UDP, but TCP might do a reasonable job. But the 4th, security. Yeah, the fact is that TCP and UDP, none of them provide security. There's no encryption at all. If we send passwords through the internet, straight using TCP or UDP, it's essentially clear text. If there's someone intercepting the message, that someone gets access to our bank accounts or gets into our Amazon.com's account. So none of these cases is good. Big money loss potentially involved. So demand is growing, therefore there is need of these secure layers. So this is secure socket layer. So what it means is that before messages go through the socket and go out on the internet, let's make sure that it's secure. Okay, so it's to provide encryption to messages that's going into a TCP socket. As a result, then we can encrypt messages using a key, or we could verify the receiver using a certificate. Okay. So this is just as important as trying to make sure that the data is confidential. Okay, because how do you know if this server that you are contacting to is indeed a Google server, right? How do you know if it's indeed your bank's server? So this is to identify whether the person you're talking to is indeed the person you're expecting. This is just to make sure that no one can understand the message. No third person can understand the message. Okay. And SSL is at application layer. Yeah, it's on top of TCP, therefore it falls in the application layer. But it's also right underneath the application layer protocol, so message goes through the application layer protocol, and then to the SSL, and then to TCP. Okay, so this picture below illustrates what I meant here. So SSL right here, right underneath the application layer protocol, but right above the transport layer protocol. Last, SSL socket API. Yeah, to implement SSL, there are APIs available for each programming languages. In chapter A, you will see Python's API to try to encrypt messages before they send messages out onto TCP socket. Now, in this semester, towards the end, one of the PAs, you will also be exercising the APIs in Golang to do secure TCP. But there, we'll be using this, TLS, Transport Layer Security Support. Yeah, this is actually a newer term for SSL. So nowadays, people don't call the security support over TCP SSL. They are all referred to as the TLS. Okay. If you think about it, this makes a lot of sense because, hey, SSL there is not really a layer. It's more a support for security. All right. Next, let's explain how TLS works. Before that, let me go back to the very fundamental computer security. How do you encrypt a message such that it can be kept as a secret? So the classic approach is the secret key mechanism. So what we do there is to generate a key, and we share the key with Bob and Alice. So when Alice has a message to send, use that key K, apply the encryption function, and it's going to generate something that's messy. So a third party in the middle here might intercept the message, but without knowing the key, it's not able to decrypt it. Bob, on the other hand, receiving the messy message, using the key, can restore the original message. Okay, so this is the classic secret key communication. Unfortunately, the secret key system is not sufficient to enable a service like TLS. If you think about it a little bit more, Bob and Alice will have one shared key. Let's say Alice is the one generating the shared key. Alice is yet to send Bob the secret key, right? The shared key. But then, hey, shared key is sent over what? TCP socket, because we don't have TLS yet. So, nah, not gonna work. So having the secret key system a lot of times does not really ensure full security unless Alice calls Bob and tells Bob the secret key offline. Okay. But hey, that's not ideal. So if you want to ensure that the shared secret key is sent right online there and no one else can see what the secret key is, we'll need this thing, the public key system. The way it works in the public key system is this. If you have a message, and if you encrypt it with the receiver's private key, so receiver's private key. So what the function there is doing is to hash using this particular value here. And as it travels through the network, receiver will receive the scramble message. Receiver just needs to use her private, public key. Oh, I'm sorry. Unfortunately, the secret key system will not work to implement TLS. If you think about it, we have one shared secret key. Let's say if Alice is the one generating the secret key. Alice is yet to send the secret key to Bob, isn't it? I mean, didn't we need TLS because we fear we send password in clear text to the other end? So Alice here is sending the shared secret key in clear text to Bob. Same problem. Yeah, so we do have a bootstrap problem with the secret key. Now, to address that problem, we use this other system on top of secret key. It's called the public key system. So instead of using one shared key, public key system generates a key pair. One is called the private key, the other is called the public key. All right, so the receiver of the secret message is over here. Sender of the secret message is on the other side. What the sender does is to plug the message she wants to send and then encrypt it with the receiver's public key. Yeah, the reason that it's called the public key is exactly because R is going to give out that key to the public, including the sender here. So this is going to scramble the origin. So this function is essentially scrambling the original bits here using this particular parameter. So the encrypted message, as it arrives at the receiver there, then apply the same function and take the received message, and receiver can decrypt with the other key in the key pair. So this is going to give the original message back. Now, the private key is the one kept by the receiver, and no one else in the world will know. Therefore, you ensure that no one else will be able to decrypt the encrypted message. So only the receiver can see the original message. So this is how the public key ensures secret exchange. So TLS, illustrated up here, works this way. Alice here is a client requesting service from Bob here, a server. So client here first sends hello message to the server. Server in response sends server's public key. So Alice here can then encrypt the shared secret that has been generated before using Bob's public key. So Bob's public key here. Then encrypted master key will arrive at the Bob side. And because Bob is the only one holding the Bob's private key, therefore Bob can restore the master key from ENS. And that's how Bob and Alice establishes the shared secret key. So in this case, you see Alice is the one generating the secret key. And from then on, all the messages are encrypted using the master secret key. And that's how TLS worked.
Good. How about that? Is it clear? Let me know. And let's move on to the second topic, the HTTP essentials. So that actually concludes already chapter 2.1. It's pretty lengthy, but it's kind of important that we go a bit slower and make sure that all these fundamental concepts, ideas are clear. So let's go ahead and start 2.1. The first application, the World Wide Web and the application layer protocol, HTTP, to support the service.
All right, we're finally done with chapter 2.1, Principles of Network Applications. Well, we did spend a lot of time there, but it's kind of important. I would rather like that we take it slow and make sure that all these basic notions and terms, concepts are all clear. Okay, so take note. We did talk about, hey, there's architectural choices. There is also transport layer service choice. And there's also definitions of messages being sent. So how many types? And for each type, what is the syntax and what is the semantics? And then hey, different types of messages might be, exchanged one after another. What is the order of these messages being exchanged? In fact, from chapter 2.2 and on, okay, all the way to 2.6, we'll be talking about examples of these applications and the corresponding application layer protocols. In these application layer protocols, you will hear me saying again and again, what is the architecture choice? What is the transport layer choice? What are the messages, formats, ordering of the messages being defined? Now, in each of these applications, you might hear, especially those that are frequently used and very important ones, I'm going to talk more about how you try to improve the performance, okay, of running these services. So let's go ahead and start the first application, Web and HTTP. Let's do a quick review. Web is essentially a bunch of these web pages interconnected. So each web page consists of a number of objects. The base object is typically a HTML file. And then in each file embedded are several referenced objects. And these objects could be another HTML file, could be a JPEG image, could be an applet or a script or an audio file. Each object on the internet, on the web, is addressed by the URL. So this is an example of the URL. There are three parts: the host name, and the path, and the file name. Okay. And the HTTP protocol there to support the web application runs in the client-server model. So the client here are essentially the browsers. The browsers is essentially requesting for web objects and then in turn receiving web objects, of course, using the HTTP protocol. Now another task the browser does is displaying the web objects. Just to clarify, passing of these messages and web object is the HTTP protocol's job, but displaying web object is actually something else's job. It's the HTML interpreter's job. Yeah, so HTML interpreter is not quite the HTTP protocol. So you see here, a browser, that program there is a combination of the HTTP protocol client side and an HTML interpreter. So this interpreter is to interpret the HTML page because there are some markups around. Based on the markup, the interpreter will know how to display a web object so that it appears properly and nicely. Now the server, web server. Very few of you guys have experience building your web server, I suppose. Yeah, so in this example we see Apache, I think, is still the most used server, but this guy here is catching up, and Jinx. Both of these servers are implemented using C and C++ socket. All right. So the web server implements server side of the HTTP protocol. So what it does is to receive requests and send back response. So that's the exact opposite of the client. It's to receive objects and send requests. So let's see the exchange. So this client up here, sending HTTP requests and then receiving the HTTP response, and containing the HTTP response is the web object. Similarly, if it's a phone, Safari sending HTTP request and server sends back an object and Safari renders and displays the object. All right, so that's HTTP, Hypertext Transfer Protocol, HTTP. And HTTP runs on top of this transport layer protocol, TCP. And the whole process is actually this. First, tries to establish a TCP connection between the web server and the web client, and then sends the HTTP messages. So before the client and the server sends HTTP messages, the client and the server sends TCP messages first. So starting from the client, initiating a TCP connection. Now, if this is a web server sitting on the default port, it's going to be port 80. And then server would accept the TCP connection, inform the client, and then client can begin sending the HTTP request. And the server sends back HTTP response. When everything is done, the TCP connection will be closed. Know that HTTP, as you see, very simple, request response. In fact, each of these requests is treated as brand new. It's very fresh. That means what the server is doing there is to not record anything about the client. So there's no information about the past client requests. Okay? And we call this type of a service a stateless service. So on the server side, there's no requirement of storing anything about the client. So this is really nice because the server does not require a lot of memory space for these information. All right. Yeah, protocols that maintain states can be complex. So this is the other extreme. You might need to maintain the past history, which can be long. And you might need to maintain history for multiple clients. How about that? That's a lot of burden in terms of a memory space requirement. And besides the service load, the memory requirement, what if the server and client each crash while the other continues to run? Then the states on the two sides might be inconsistent, and they will have to resolve the conflict somehow. That's the worst, right? So should you trust the client or should you trust the server? This is one of the classic car problems, all right? HTTP connections. There are actually 3 flavors of HTTP connections: non-persistent HTTP, persistent HTTP, and third, persistent HTTP plus pipelining. All right, so let's start from the most basic, the oldest flavor, non-persistent HTTP. This is implemented in the pioneer versions of HTTP, let me call it that way. In that, you send one object per TCP connection. So the clients and the server sets up a TCP connection, and then you send one HTTP request, you get one web object, and then you close the connection right after that. So to download multiple objects, you need to create multiple connections one after another sequentially. Now in persistent HTTP, the main idea is, well, why do we keep opening TCP connections and closing them? Why don't we just reuse the TCP connection we have started in the first place? So in persistent HTTP, client and server establish the TCP connection, and then first web object exchange, second web object request, and the object response exchange, and so on and so forth. So one single connection to send all the objects. All right. Now, the basic persistent HTTP mode works more like that. So you have one exchange to establish TCP connection, and then it's just object 1 and object 2 and then object 3. Okay, but the thing is this: when we establish the TCP connection and sending out the first request for object 1, really, before the object 1 is being transmitted back, you see, client over here, it needs only this amount of time to send the request message, right? Client is immediately left idle right after that. So why don't we send the second object's request, the third object's request, and the fourth object's request subsequently and immediately? That way, you just need another exchange like this and, just a few more transmission time. Then we're done with everything. Unlike here, for each object, you need this much time, and the second object would wait this much time, and the third object waits even more time. Okay, so this here is the persistent HTTP plus pipelining. Nowadays, when people say persistent HTTP, the implication is that, hey, it's persistent HTTP with pipelining. And by the way, this is HTTP, the 0.9 version. And persistent HTTP without pipelining, that's the HTTP 1.0 version. And the one with the pipelining is the HTTP 1.1 version. All right. Now let's go through the animation for the very standard non-persistent HTTP protocol's behavior. Let's suppose we are looking for this object here. So the URL contains the host name, the path, and the file name. And let's see that this base file here contains 10 reference objects. So there are 10 images embedded. Step number 1, the TCP establishment. Client here initiates connection request. Server sitting at this location at port 80 will accept the connection and then send back a, sure, open it message. Second exchange is the client sending the request message. All right, so in the message, embedded is the URL. All right, so that's going to go through the socket, and URL right there in the message. Server will receive the message and sees the URL, finds the path, finds the file name, and therefore extracting content and generate the response message. And that response message is shoved again through the socket back to the client. Now, immediately after the response is sent, the server closes the TCP connection. HTTP client here receives the response, parse the HTML file and displays it. And in that process, it's discovered that there are 10 more reference objects to download. And the client then will repeat step 1 to 5 again and again and again, 10 times until all 10 objects are downloaded. And the time to do that is pretty long. Let's try to count the amount of time to complete the entire download. And we call that the time to download an entire page being the response time. Before calculating it, let's define this term. RTT, which stands for round trip time. It is the time for a small packet goes out to the other end and comes back, out and back. So it's a round trip in a sense. So client over here, server over here, to initiate a TCP connection, the connection request go. Connection established, granted messages come. That's 1 round trip time, right? So 1 round trip time for initiating the TCP connection. And it's another round trip time to send HTTP request and receiving the HTTP response. So this part is 1 round trip time. But the dark, thick square here, this is the time it takes to transmit the file. Okay. So when the object is very small, this is very narrow. When the object is large, this could also be quite wide. So let me fill it up. So the object itself could be big. The transmission time can be long. So the shadow part is the file transmission time. So the response time to download just 1 object using non-persistent HTTP is 2 round trip time. 1 here, 2 here, and then the file transmission time. Now we can try to account the response time for that page we were loading, the something.edu, the object there. So we have the base and then 10 more objects. So altogether 11 objects. If we're running the non-persistent HTTP connection, then we have 2 round trip time plus the transmission time for object number 1, the base object. For each of the 10 objects, we do more. Okay, so the transmission time might vary a little bit from object to object, but round trip times remain the same. Right, so there are 10 of these. So 20 22 round trip time. So 10 of these plus this one over here, the base. And yeah, the sum of the tx, okay, and depending on which object it is for all I. All right. Now, but for persistent HTTP, the server is going to leave the connection open after sending response. So subsequent HTTP messages between the client and server will be sent over the open connection. Client can send requests, as I said, right? Persistent HTTP without further clarification, it's the persistent HTTP with pipelining. So the client here will send all the 10 requests as soon as possible. Okay. So in the end, it's just one round trip time plus the transmission time of all these objects. So altogether, just 2 round trip time. First is to establish the connection. Second is to download the first object. Okay. Third is to download all the rest of the 10 objects. So it should be 3 round trip time plus the transmission time required to send all these objects. So 22 versus 3. Big win over here, right? Yeah. So this is in HTTP version 1.1, the most up-to-date version.
Good. Hope that's clear. And we do have a question here from Pei An asking, how does the encryption-decryption using different keys in TLS work? So I'm not sure if I get the question. So my interpretation of the question is that how does encryption works? Right? So I suppose when you say different keys, you meant different encryption mechanisms. So the answer is that, as I described, all these encryption mechanisms is actually taking the data and then plugging a parameter and go through a certain calculation, go through a certain function. The basic idea is to find some one-one function such that it's hard to reverse. Okay. If that addressed the question, let me know. If that does not address the question, just keep asking. All right. And now we move the last part of the lecture today.
All right. We'll be switching gear just a little bit and talk about the messages in HTTP protocol. This is actually a very important part of an application layer protocol design, and we'll be using HTTP as an example to talk more. For all the application layer protocols coming up the rest of the chapter, we're just going to go real quick. Okay. Now, it's also important to spend some time here to talk about the messages in HTTP protocol because in the second half of the semester, you'll be implementing a web server. That means you will need to be able to interpret messages coming from the client. And you will also need to be able to generate the messages you need to be sending to the client. Okay? So, hey, receiving from the client, sending to the client. Yeah, those messages happens to be the HTTP request and HTTP response. Request is the one coming from the web browser to your web server. Response will be the messages you generate and send back to the client. All right. So there are 2 types, easy, and that is about the easiest part. Now, what comes a bit complicated is next. Let's look into an example of the HTTP request message. Here's one. I know, a bit messy, isn't it? Okay, but hey, bear with me. That's reading. Get index.html http/1.1. Okay, not so bad. Host column worldwideweb-net.cs.umass.edu. Not so bad. I can probably guess what that means. User agent column again. Firefox. Oh, that's a web browser implementation, isn't it? 3.6.10. Oh, probably the version number of the browser. being a Firefox browser. And so, hey, accept language, EN US, probably English, US type of English. Not so bad. Keep alive, 115, connection, keep alive. So maybe the connection is this type, the keep alive type. And maybe 115 is to specify how long the connection should be kept alive. So, until now, your experience is saying this. It's reasonably readable, human readable. It doesn't take a computer to read and fully understand it. So yes, HTTP messages, including requests and responses, they are all text-based, very readable. Let's take a closer look at the syntax of HTTP request message. First is the request line. It's only a single line, 3 tokens, separated by 2 spaces, one over here and one over here. First token indicates the command the client is issuing to the server. So get here is the most classic command. Second token here indicates which object the client is wishing to download. So here you see the path and the file name of the object. Third token is very straightforward. It's simply telling the server the version of the HTTP protocol the client is implementing. Now, header lines. Syntax is also quite straightforward. Column in the middle. Before the column, this is called the attribute or the field name. And whatever comes after the column is the value of the attribute or the value of the field name. All right, so user agent is a well-defined attribute in HTTP. It indicates what implementation the browser is and the version of it. So user agent indicating the meaning being user is using a browsing agent called Firefox, and it's version 3.6.10 of Firefox. Okay, similarly, keep alive, also a predefined attribute. And the value 115 is saying that let's keep the connection alive for 115 seconds if there are no messages being sent. Connection indicates the type of connection the client is wishing to establish. It's the keep alive kind of connection. And so you see the syntax and a little bit of semantics of HTTP request. Next, the general format. Okay, now with that introduction, with a specific example of HTTP request, this will be slightly easier. You see here, first is the request line. And then we get a whole bunch of these header lines, and it ends with what? CRLF. Okay, in fact, at the end of every line, CRLF. Okay. And in the request line, we have 3 components: the method, the argument for the method, and the version. Okay. Some comments might not contain the second component. All right. And you see here, for each header line, we see what? Pair of attribute name and value. So in the slide, we see this is the header field name. So those attributes are sometimes also called the fields, the field names. So attribute value or field name value. Good. So lots of these. And hey, this is the thing that we did not see in the previous example. Yeah, occasionally you do need to have a body in the HTTP request message. And this is what, if you recall, the post comment. We're sometimes posting content, posting data onto the server. So those data, those information to be communicated from the client and to be registered at the server will be here in the entity body. So real data generated by the user is here. Okay. So officially, in general form, the HTTP request comes in 3 parts: request line, header lines, and body. But for most of the HTTP requests, there are just 2 parts: the request line and the header lines. Now, let me add a little bit more. First, the post method. You've heard me. There are sometimes web pages that you need to fill forms, okay? Input names, usernames, potential passwords. Okay, those input are uploaded to the server in the entity body. There's another way of doing that recently. Okay, it's called the URL method instead of the post method. What you do there is, hey, you could be clicking just buttons, okay, a certain link, in fact. What the browser does there behind the scene is more like this, okay? Requesting to the server, all right, okay, but it's actually sending a phrase like this. Instead of a file name with the path, okay, so instead of having a path something, and then something.html, so it's a very weird form of HTTP request. Okay, while we know this is more classical, but these days we see this more. Okay, animal search question mark and then something and something. Okay, so this is actually a query. Okay. Unlike request sounds more like requesting for a service, requesting for a file, for an object. But clients often query the server for a service. Okay, for example, look up a database. Exactly. So in a way, the World Wide Web is evolving from a huge hard disk, a global distributed hard disk, to a global distributed database. Okay, so in the HTTP request there, we are actually sending a query. This is the name of the query. And this is the input to the query. So this query obviously contains two arguments in order to execute, for the server to execute. All right. It's using the get method instead of the post method earlier. So this type of a service request is using the get method, but in HTTP request message. And the input is exactly in the URL field in the request line. Okay, and it's this way. Yeah, the query name and then the arguments for the query. All right. And the last slide about HTTP requests here is quite straightforward. What it says is to tell you again what are the comments, okay, possible in HTTP request line. In version 1.0, we see get, we see post, we see head again. Okay. But this is all that HTTP 1.0 supports. In HTTP 1.1, we extend the comment options from the 3 classic ones to add 2 more, put and delete. Okay, let's go through these 3 other comments. First, the head comment. So this is usually for a web client to send sort of initial HTTP request to the server, and server will send some response back, but only to tell the status of the server or the specifications of the web server, and leave the actual web object the client is asking for out of the response, so that the response is very short. And what's contained in the response messages are just all the essentials, like, what is the version of the web server program you're running over there? What is your IP address? What is the time date? What is the time date, the object that the client is asking for being modified last? Okay, things like that, the essentials about the server, about the object. So that when the client receives a response like that, the client can plan a little bit better ahead of time how the client does the requesting. Sometimes when the file is really large, the client might try to dissect and then do the requesting slightly differently. And put here, this one is actually quite forward. Just to upload the file, in the entity bar, upload this file too. Okay, so it's working pretty much like the FTP. If you recall FileZilla, you are dragging a file to the server, right? So it's uploading a file to a specific path on the server side. So put here implements file upload. Delete, deleting a file. So FileZilla also allow you to do this. So essentially, HTTP 1.1 is to extend the original HTTP to include all the file uploading, downloading services, because the original HTTP only does file downloading, not quite the uploading. Now, when HTTP 1.1 is available, FTP protocol quickly loses its popularity. Okay? And that's why we rarely use FTP these days, because HTTP, the web browsers can do all these for you. All right, so this is HTTP request.
Good timing. Yeah, so quiz number 7 is right here. Okay, so what you're asked to do is very simple. Let's suppose that we actually captured a HTTP GET message, HTTP request message with the GET comment. So it looks as what I depicted in the square there. Okay, so Q1 there is asking, what is the URL of the document or the object being requested by the message? Is it a non-persistent or persistent connection being requested? All right, so think about it. And you have some 3 minutes time to type up what you think the URL is and whether you think this is a persistent or non-persistent HTTP connection the client is requesting. Good. So let me come back to the questions that are being asked and addressed in the meantime. So first is, Rocket asked, what does CR do, right? If there's already a line feed. It seems that if we do new line, we simply go to the next line and start from the beginning. But what's character return? That has something to do with the mechanical typewriters in the early 20th centuries or late 20th centuries. The way it works is that when you hit character return, it only goes back to the head of the line. So you have to hit line feed again so that the paper rolls a little bit and you may then start typing from the next line. So the Windows designer particularly keeps the mindset. That's why in Windows system, you have to use character return plus line feed to ensure that you go to the next line and start from the head of the next line. But in Unix-based system, that is already abandoned because really there's no need of combining two characters just to do the same thing. So it's just \n in Unix system. So just be a bit careful when you're working on the PA 6 and 7, all right? So that's actually, PA 7 and 8, where you need to interpret an HTTP request message and generate an HTTP response message. Now the second question from Rocket here is asking, do the requests always need both the CR and LF IC? So on the Windows system, I think maybe you want to be careful to do CR and LF, but I'm not sure. It might have something to do with how the operating system versions is handling a slight variation like this. So I have very little experience playing with the Windows system. So Rocket, you can try it out if you generate your messages, always ending with just the LF without the CR, and see if you run the server on Windows, whether it will accept it. There is potentially a compatibility problem, right? I hope that addressed all the questions, and it's time for today. I'll see you again tomorrow morning. It's 10:20. Good. And quiz number 8 is coming up actually the first hour of next day. So just that you know. Good. I'm just going to keep the live session for a few minutes in case you want to type up whatever you want to say for quiz 7 real quick here. That way you avoid going back to the FB group and then try to comment there. Good. And by the way, for those who wants to get lunch quick, just feel free to go. Okay, only those that wishes to stay and type up on the live chat for the quiz solution, then stay. Very good. Zixian, and you are, I think, team 7, if I recall correctly. Great. Team 7 done with quiz number 7. Oh, and by the way, Zixian, that is only the past name, okay? So URL actually contains the host name. But hey, it's okay. Now you know. Okay, let's see. Darius, team 12. Persistent connection, definitely. Can you see the host name? Yeah, you can. Good. Okay, I got team 4. Yeah, same issue there. Being an HTTP 1.1 has to be persistent, right? It is just the version that, or is that wrong? Just, I agree. I agree. Uh-huh. Well, but you will probably have to turn on a flag or two to disable it. Yeah. I think it's all in the implementations of the servers running HTTP 1.1. It's just that, yeah, I mean, one could probably configure the server such that it's not running the persistent connection mode with pipelining. And I think also if a server running the 1.1 protocol and running into a client, running into a browser that's 1.0, chances high that the server will be just using the persistent connection mode, yeah, without the pipelining. Otherwise, the client might have trouble receiving the web objects. Yep. So there are cases where even though the server is implemented based on HTTP 1.1, but it might not run in the pipelining mode. Okay. Okay, so we have just 2 more minutes. I'll have to go then. Good point, Rocket. Also, if an HTTP 1.0 client is trying to connect, the server definitely needs to fall back to which does not do longer than 200 characters. There you go. And ing here is using persistent connections is kept alive. Very good. So I'm not sure which team are you. RNG, so let me just track that. Team 4. Okay, ING Silvercraft, whoever you are, can you let me know your team number? Okay, real quick. You can send the first half of the message. Interesting. So maybe it contains some words that look suspicious? Okay, good, I got you, 13. Yeah, but it's okay, because other teams are actually sharing their solutions, and I guess it might be that you guys are typing up a host, gaia.cs.umass.edu. I don't know why that is sensitive. You do know that Google live chat, they actually censor whatever goes on the live chat. So it could be because of that. Maybe, yeah. Maybe some commercial, spams. So I guess that's what's going on. Okay. So those give the slightly wrong answer, not exactly accurate answer, gets to say, I get to see the answer. But those who are actually correct, perfectly correct, will not allowing me to see the answer. I see only Q2. I think the same issue with the Darius. Okay. And by the way, if I mispronounce your name, because you guys are all coming from different regions of the world, okay, I go with the American accent, so I don't know. Yeah. Let me know if you're not very comfortable with me mispronouncing your names. Good. All right, good. So I have to go. Then the rest of you, if you're still typing, feel free to copy and paste whatever you're typing to the Facebooks and add the comment below the quiz 7 picture. And that's call it a day. And I'll see you tomorrow.